Welcome to the Mound Science and Energy Museum seminar series. This is our second in person for 2021. It will also be our last in person in 2021. But we will plan on doing it again starting in January 2022. So my name is Bob Bowman. I'm on the board of the Science and Energy Museum Association, and so somehow I got stuck with the job of trying to coordinate seminars. And I guess they decided to do that rather than have me give any more seminars. But I'm very pleased that we're going to have the talk today by Ray and Bob. I was a user of the special equipment. In fact, Ray is a co-author of one of my papers. You may not know that, but you are. But we did a lot looking at radiation damage and effects in metal tritides, and using that technique to analyze the gas composition. And so it would complement our nuclear magnetic resonance studies and other things that were redone. So without me going on about how great this technique is, it's a unique opportunity to see something that was very developed and adapted at Mound. And so Bob Ellefson will begin speaking on the all-metal automatic Toepler pump for quantitative gas transfer.
Good, thank you, Bob. You've probably seen this long enough. Oops. Okay, as Bob mentioned, here at Mound we had many projects that involved the quantitative measurement of gases released in some kind of a chemical reaction or releasing hydrogen from a metal hydride. The actual case that Bob was just talking about. So this is kind of an outline of the talk that we're going to give tonight. All of the details and data comes out of papers that Ray Baker has written, and we discussed them in the last month or so often. And from that, this is what we're distilling as a practice that went on at Mound of making a new instrument that is automated to make our work easier so we can do other things. And so the automation of the Toepler pump is the function we're going to talk about. So we'll talk first about what are these quantitative measurements that we need to determine moles and grams of gas. And we'll talk about August Toepler, who invented a nice glass mercury displacement pump in 1868. So it's a very old technology, but we're giving it new legs by making it safer and more generally automated in this talk. So the stainless steel Toepler pump and its automated design control is the focus of our first section. We'll talk about the design of the pump, the fabrication of it, and the fabrication of the control system. And then some of the valve designs that Ray had done to make it operate and seal more efficiently. And then the automation of gas collection by the use of the pump and measuring the pressures that it evolves. And then we talk about secondary containment for the measurement of tritium-containing gases. As the all-metal Toepler pump, it is safe to use it in the presence of radioactive gases. So we'll also talk about some applications of it. One of the primary ones is looking at hydrogen storage with hydrides. Uranium hydride is an example where H is one of the hydrogen isotopes. And here at Mound we had all three. Normal hydrogen, which is protium, and then there's a hydrogen with a deuterium neutron added, and then tritium with 2 neutrons added to the proton. It's still chemically hydrogen, but now it has 3 times the mass and is radioactive. So the handling of it is different, but the chemical storage of it is the same or similar for all 3 of those species. We'll talk about the use in component evaluation for post-test gas transfers and measurements. preparation of accurate gas mixtures by partial pressure addition. And in order to do that, Ray had to develop a method for generating HD of high purity so that we could make the mixes that we wanted to use in our mass spectrometers. And then finally, we'll talk about the publishing that has been done on this to make it generally available, and the patenting that resulted from some of Ray's valve research. So who is August Toepler? Well, really he's best known for the electrostatic generator that you turn a crank on and you generate very high voltages, like 70, 80 kilovolts, which is enough to excite an X-ray generator and produce X-rays that can give you film illumination and do X-rays. So the early X-ray source was built by Toepler, but he also made the glass Toepler pump in 1868 in Austria. And here in the center is what we're talking about for a glass Toepler pump. You can see the mercury level inside. This is an example of a real Toepler pump functioning, and it's raised the mercury all the way up and compressed gas into this volume. The gas that was down here ends up being transferred and locked in place in that volume. So you're already getting an idea of how this thing might work. The fluid for the piston of this is mercury. Now, you may remember back when you were in middle school or something like that, you somehow got a hold of a couple of droplets of mercury and you were chasing it around your desk, and that mercury is a liquid metal at room temperature. And you can also freeze it. But at room temperature, it's a liquid metal. And so you might ask, in 1868, was there much mercury around? And the answer is yes. In fact, right next to Austria, where Toepler was living, is Slovenia, which has the world's second largest supply of mercury. So here's mercury, and it dates back this little town of Idrija, Slovenia, to 1490. And the highest production mercury mine in the world is in Spain. So mercury's been around for a long time with its interesting properties of being a liquid metal. Okay. So let's move to what are these gas measurements that we want to make. So this is the only physical chemistry we'll talk about tonight, but it's one of those things. I learned all of these rules of chemistry and physical chemistry and this kind of thing. Never did a measurement that ever said you could measure what a mole was. A mole of gas is, looking down at the bottom, at room temperature, a mole of any gas is a collection of atoms. 10 to the 23 atoms, that's a lot. 1 mole at room temperature and atmosphere occupies 22.414 liters. And for us here, that would be a cylinder about 12 inches in diameter and 12 inches tall. So it's bigger than your average bread box. But it's a tractable size of numbers. So typically, we would have fractions of a mole of something that we can quantitate, and we would collect it. So how do you collect it and measure it? This is an example. Let's say that there's some uranium hydride here, and you're heating it up and the gas evolves off is hydrogen, and you have a pump that takes that gas and moves it over into the outlined red space. And by closing the valve, you can define a particular volume. So that gives you V for calculating what's the volume occupied by the gas. The pressure tells how many molecules per cubic centimeter are there, producing, when they run into the walls and things like that, producing pressure. So you need that pressure and volume. And the third one you need is the temperature. Now the temperature is defined as the Kelvin temperature, which if you let the Kelvin temperature go to 0, all of the gases would collect in a puddle in the corner, or probably as a solid brick of ice. So the idea is that the gas depends inversely on the Kelvin temperature. So what is the Kelvin temperature? It's the temperature in centigrade, like say right here in the room, is about 24, 25 centigrade plus 273 to get the Kelvin temperature. So there's some transformation to do. But if you look at this, this pretty well looks like something you could set up in some kind of a computer program, fill in the blanks with the numbers. You have a prescribed way of calculating things that everybody uses, so you can agree on the results that comes as to how many moles are there. One other, or two other little things. The Z factor is the fudge factor, and this is related to the compressibility of gases, which varies with the gas and with the pressure that it's at. But typically, it is in a way to account for things like the fact that molecules are a particular size and they do occupy some basic space and can't get it any smaller than that. So that is the absolute compressibility of it. But in fact, if you have smaller amounts of high pressure, you can calculate what the compressibility is. And R is the universal gas constant in the appropriate units to make this come out in moles. So that's the kind of data we're looking for. We're looking for a known volume where we can measure the pressure, the temperature, and we can also extract some of the gas and send it to the mass spectrometers who analyze the gas and give the composition back as a report to you. So from that mole percent composition you get, you can take the mole percent divided by 100 is the mole fraction, times the total moles, times the gram molecular weight for the gas species X sub I. So again, that's more than you ever want to know about how to use these things, but it is the basis for why it's important to actually do these measurements. Okay, the Mound all-metal automated Toepler pump solves really many problems for the glass Toepler pump. One of the issues with the glass Toepler pump, as you might expect, is breakage. This can happen from the mercury violently being spread around by having too much pressure on it or something like that. Accidents can happen. Or other breakages, like you're working in the fume hood and you're reaching for something and you whack the glass and it breaks. Okay, so that's why you put it in a fume hood, so anything that's evolved or something like that. Brady, have you had experience with breakage of Toepler pumps?
Just once.
Go ahead, sir.
Just once. I have, and that happened to be at night. You turn the pressure on the inlet system, and that's servicing the pump to on the same vacuum. So when it broke, the mercury stayed in pool.
Closer a little bit.
The mercury stayed in pool.
Okay, so it was broken glass, but no
No
mercury
mercury
all over.
spillage because the same pressure was on both sides.
So what did you think you should do after that?
Well, that ended the system right there. But what I learned from that was, I took the mercury out. I was surprised we didn't get alarm levels in the room when this happened, but we didn't get any. So I took the mercury out of that and poured it in beakers and had health physics take wipes through it. They couldn't find any wipes, any contamination.
Yeah.
So we could use the mercury over again.
So this was an early example where some tritium was involved in it. It was done in a fume hood, which was the safe rules for the day. And but the interesting thing is the mercury did not absorb any of the tritium, so it didn't wipe, and it was safe. So presumably, at the end of Mound, you could have recovered all the mercury, but I don't think we did.
Yeah.
So, let's continue. Okay, there's some other things that can happen. Incomplete gas transfers, gas leakage, irregular functioning of the valves, and difficulty handling moderate gas pressures. You don't want to stress glass with too high a pressure, but you could easily have an accident and have the pressure jump from like 20 psi to 200, and then you'd have glass all over the place. So there are things that can happen like that in a laboratory situation. The other one that's interesting is electrical arcing of the sensing contracts with the mercury. The contacts were there to indicate that the mercury is up here, and now you can switch and evacuate it. But it also involved glow discharge at low pressures. So you have low pressure mercury vapor, but you also have other species that glow that can be there. And I think you saw one of these also, Ray? Did you see the glow discharge?
I saw it twice, and it's sort of scary because it's like taking your picture as a flash, like a flash.
Think of a xenon flashlight. Yeah. And so
Quite scary, really. Nothing happened though, really.
again, so two messages that maybe we ought to build an all metal one. So the stainless steel that we use provides a safe containment for the mercury, for the whole expression, any of the gases, and certainly for tritium also. Okay, how do they work? The pumping function of a glass Toepler pump is basically duplicated with our all-metal Toepler pump system. So what is the basic motion? There are a two-way valve here that you can have compressed air that pushes down on this mercury pool. There's a barrier in between, and then there's a siphon that takes the mercury up through here and allows it to accumulate up here. We'll see a little more of that in a minute. And so as that goes up, the gas that came in from some source here gets trapped by the mercury sealing off any further gas coming in, and then it compresses that gas to go through a mercury valve lock into a collection volume. And that's the basic function that's been used for years with this. So we have the same thing in the Mound Toepler pump. This has a mercury reservoir down here that has about 45 pounds of mercury. And mercury is a heavy metal, but that sits there, and at the end, by the vacuum, it comes up to a frit and it gets sealed off here with this check valve. Okay, so that's one starting point. At that point, the channel to the gas source is free to fill up this to the same pressure as whatever's there as a gas source. Okay, then we start pressurizing this part of the pump. This mercury level goes down, mercury goes up the tube and starts to fill this volume, seals off this supply, and continues to go up. And the seat here will allow the mercury to eventually come up to a frit and get stopped. And that's the switchover point to when you go back to vacuum and lower the mercury to get another charge of gas by lowering it to this level. We'll get to the details of those in just a second. The construction of this was done with stainless steel, and the bottom is a cup that is, well, it's approximately 4 inches in diameter and 4 or 5 inches tall, and it's hydroformed out of stainless steel sheet, like a 16th inch stainless steel. And similarly, there is a conical part shaped for the top of it. And then there's machining done for the ports to come in and welding of things. And then the bottom plate and the two top and bottom, they all get welded together with the full penetration weld on it to make a nice strong seal. And then you have a pump. So let's demonstrate the pumping action. Whoops, wrong way. Pumping action with this sequence of events. First, there is a nitrogen pressure cycle where nitrogen is used to push down on the mercury column, and that forces the mercury to go up through the tube and accumulate here. And as that accumulation continues by keeping the pressure on, you get to a quarter full where you seal off the source tube, and you keep adding pressure to it. More mercury goes up and ends up here, and eventually at full pressure you have the mercury pretty well depleted, and it's all the way up and stopped by a check valve at the supply and at the exhaust to whatever the collection volume is. So at that point, there's no flow of nitrogen because it's deadheaded against the frits up here. So we'll see in the control system what we find then. At that point, we need to define some way to switch from nitrogen to a vacuum. And then we go to the evacuation cycle, which starts with this stuff nearly full. You start pulling a vacuum on here. The mercury rises, and this part goes down. Eventually it gets low enough that you get a new dose of gas, and the vacuum goes to zero because the density of the gas across the pressure switch goes to zero. So anyway, that's the sensing that we do, that the delta pressure on the sensor goes back to zero, and then you start with nitrogen again. And you go around in a circle, and well, actually like this, I guess. But it's a secular type thing which lends itself to total automation. So how do you do that? Well, the pumping cycle switches from pushing mercury to lowering the mercury level using a differential pressure sensor that looks like can actually measure the pressure difference from one side of an orifice to another. This is the pressure sensor. That's the brains of the whole switch. We'll have them up here. You can come take a look at these things. On this drawing, this is where the pressure sensor is located. There is an orifice here that the gas goes through, and by throttling it down like that, if there's a flow of gas, there's quite a pressure difference from one side to another. So that means that the gas is flowing and you want to keep pressurizing mercury up. When that flow stops and the differential pressure across here with no flow, it goes to zero. High pressure and high pressure, the difference between them is zero. So then at that point, we switch to evacuation, lowering it, and again, delta P goes to zero because of low density of the gas with the full evacuation of it. Then again, it switches to pressurization, and you just go cyclically between these. So the two states are delta P equals zero. Use this switch between nitrogen pressure and then switch to vacuum. So the two switches are controlled by solenoid valves selecting the paths. So this is the whole unit, the physical unit. The pressure sensor is right here. And the gas flow is, there's nitrogen pressure on this end, 16 psi, and on the other end there is a good vacuum that is constantly available. And these solenoid valves switch between whether you get pressure going through this to pressurize or a vacuum to it. Yeah, I got one slide out of order here, looks like. These are the solenoid valves. They're not very large. They're about 3 inches in diameter, or on the edge for each of these. And then there are Teflon channels that we'll look at in a second. That determines the path of the gas. So pump cycling is accomplished by flow control of the nitrogen pressurization, which is the red lines here, and the evacuation of the mercury pool, which is the green lines here. So let's go through a cycle. Basically, between each of these solenoid valves, there are like 3 Teflon or metal apertures here. And that is to direct the gas through the valves in the proper way. And so these are designed by Ray and figured out what they ought to look like. And we had them made and put it together. And so what that does is during the pressurization cycle, the gas follows the red line path through an orifice here, and you measure the pressure difference from one side to another. The lower side of it is lower. So the red gas goes here to the actual Toepler pump. So the gas will go to this line, which is the pressurization service line of the Toepler pump. Then when you have reached full mercury, you switch over to the evacuation. And so the vacuum pulls the vacuum, and so that the gas in the green lines moves basically in the same direction, so that the pressure differential across here, again, is high on one side, low on another. And the switchover point when you achieve vacuum occurs with the dP being in the same sign. One side high, one side zero. So that's the basis of the whole control system, so it's fairly compact, which is a nice thing to always have. So the goal of this is to automate the pumping operation. So Ray defined the 2 states of pressurization and evacuation triggered by the pressure differential going to 0 signals as indicating the time to switch state from whatever you're at to the other one. and just back and forth is how the logics work. So with that, some people from our electronics department, Matt Hartzog and Steve Huff, worked on the logic and the wiring of this to make the unit execute a start pumping by pressing a button until the operator or pressure readings determine that the gas transfer is over, like the reading stays constant in the receiving vessel, there's no other gas to come. So you can use that as a sense to stop it, or you can press a button that says stop. So that is basically how the thing works, and yet you can press start and stop, and it will continue to pump with cycles of mercury during it. Now, being opaque with stainless steel, you can't see it go up and down, but you can see the effects of the pressure and the functioning of it. So where was this used? Certainly in the metal hydride research groups, they needed to measure what's the stoichiometry of hydrogen absorbed on a particular metal. So they were interested in decomposing the metal hydride to get the hydrogen, measure it, and relate it to the mass of the metal. The analytical chemistry group did various chemistry tests. Component evaluation, like these pumps, as a way of taking the gas from a function test and transferring it to individual measuring volumes as a way to automate their measurements of where the gas went during the function test. So a new one that we had is Ray developed a method for making HD species, which is hydrogen deuteride. And instead of being H2, or D2, it's HD, which is the statistically twice as probable that would occur when you have a chemical reaction. We'll look at that in a second. So we're making accurate mixtures by precise addition of gas feed components, and we're going to look at each of those briefly. One more thing with the valves. Ray had worked on a variety of valves, like ceramic valves for the gas inlet, and the mercury would float this ceramic up and seal off, and then the tungsten carbide would keep the gas that you had been compressing in the volume, keep it from going backwards and leaking back into the pump by having a tungsten carbide ball on top of a Haynes ball. Why would you do that? Well, you look at Haynes density, it's 9.13 grams per centimeter cubed. So it's a stainless steel that is a little more dense than stainless steel, or ordinary steel, I should say. Then you have mercury, which is 13.6 grams per cc. And basically what that says is Haynes 25 floats in the mercury. And as it floats there, you start to raise this, and the conical seat of the valve makes a very good seal because there's a little mercury there to wet the surfaces, and you get a good seal. And so this is on the service line where you keep changing between nitrogen and a vacuum. So the vacuum cannot pull mercury up into it because of the check valve that's here. Ray is a good experimentalist, so he tried a lot of different things. There's one more we look at too. But basically, this is the one that's chosen and we'll focus on because it has the least probability of leaking under any conditions. The other one that we looked at was soft seats, and we'll look at the patent on that. But there is some risk that if you have bubbling of the mercury, it could get by this and before it gets seeded. So we're again back to the floats and conical float designs, chosen as best due to valve seals. Bad spelling of valve. Okay, let's look at the first application. One use of the Toepler pump is to measure decomposition gas released from metal hydride. Most metals react with hydrogen and make a metal hydride. So at Mound, we studied different ones for different applications, including storage of hydrogen for hydrogen-fueled cars. But basically, Mound studied metal hydrides for hydrogen storage and other applications. That was interesting to DOE. Heating grams of a metal hydride can generate the gas. It's kind of reversible. So decomposition of a metal hydride, an example of that would be uranium hydride. We stored a lot of our hydrogen in any form, any isotope, as a metal hydride using uranium beds. And so, so what you can do to find out how much hydrogen is on here is you weigh the quantity of the metal hydride, you put it into a heater. This is a source of heat. You monitor the temperature. Temperature needs to be 300 centigrade or higher, often much higher. But then the gas evolved can become the source of the gas to a running Toepler pump that puts it into again, a known volume outlined in red, so that you say all of the gas is going to reside there, and we can do a measurement of it. And if there's a correction to the frit, you can add that volume possibly with it also. So that's an example of doing a decomposition of a metal hydride. And the next one we looked at is production of the HD feed gas by reaction of water vapor with lithium aluminum deuteride. I think one of my techs, Dwayne Spadafora, had been making HD in an apparatus in our lab. He was really glad when Ray came across this method of making HD. Okay, how do you do that? Well, we have a little supply of liquid water in here, and you attach it to this T, and then you can establish a path through a hot iron bed to a vacuum system. Close off, you don't want to supply it to the liquid nitrogen. But you can evacuate any of the air components through this line, and any water vapor that comes along with it the oxygen gets scavenged by the iron, and you end up with hydrogen just being pumped away. So you pump for a while until you've got this thing just kind of bubbling because it's evaporating water and the air is all gone. You close this valve and then divert, and the valve's up here, probably there. Then you start drawing water vapor through the lithium aluminum deuteride and have that go through liquid nitrogen traps, which freezes out any water vapor. So the only thing that goes to your Toepler pump and into the holding volume is the HD hydrogen. So it's high purity hydrogen of the species that you want. So that's the basic design of the thing, and Ray did this with a small quantity of the material to get a proof of principle type of thing. Then the next thing is to look for how do you make this more efficient, produce more HD. The answer to that is you make a bed that has more lithium aluminum deuteride in it, and a wider area so that it can percolate through that, have a greater contact of the water vapor with the deuteride, and the effluent of HD increases. So that is basically what was used to gather the quantities of it. When it stops producing gas, when you have enough pressure, you close this valve close the source of this and pump this gas through the Toepler pump, close this, and let it go into the product container. Okay, so what did he produce? This is an example of 7 batches of HD that were product. In the measure of the goodness of the reaction is, you should see something about 98% HD. And so most all of these are, except this one, and that was the first one. So it's probably a conditioning thing. But still, once you know what the composition of this is, of HD, you can use that and the other species to add together with whatever mixture you're going to make. That's the next thing we do, is the all-metal Toepler pump was used to add gas components to make to a common volume to make a mixture. And you say, well, okay, that sounds interesting. Why is that any better than blending things together by other means? And the answer is the pressure gauge for the accumulation volume is an ultralinear pressure gauge called a Ruska DDR 6000. They were coveted at Mound. They were used as the primary transfer standard for going out and checking the performance of your pressure gauge because it was the absolute gauge. The way it worked is it had a spiral tube of quartz that the gas was on the inside of the quartz, and when you added pressure to the quartz, it would try to unwind the coil. And so that would exert a torque, and you could counteract the torque with an electromagnetic field, and you measured the voltage to counteract it. That gave you an ultralinear pressure response for this. These gauges are primarily used for well logging and deep hole drills and things like that, but we found out about them, and we use them for making these standards. Okay, so how do you do it? Well, you arrange your feed gases like H2, helium-3, HD, and D2. They are attached to a bank of standards. And so if you want some of that gas, you open one of the valves and use it as a feedstock to the Toepler pump, back up into the volume, which has a water jacket to keep it thermally at a known temperature. And then you measure the pressure as the gas accumulates by the additions that you're doing. And so basically, how you control the composition of it is you calculate ahead of time what's the pressure for the H2 component that I want. You add that partial pressure. Like here it's 3.44 torr. And this is 1,000 torr gauge, and it is accurate to this second decimal place of the torr. Then helium-3 was the next component, 43.06. The HD is added with 154.49. And whatever deuterium and H2 were there, they get added to this in the ultimate calculation of what's there. So then the last thing to add is the major component, which is deuterium, D2. The reason we put them in this form is hydrogen molecules talk to each other by collisions. And there is an equilibrium distribution for a particular composition. This one is 6% hydrogen, 90% deuterium, and 4% helium. Okay, helium doesn't have anything to do with it. The HD, they actually, if you take the HD squared divided by the H2 and the D2, you should come up with a number like 3.235. 3.226 is the theoretical. We produced a mixture that is very close to equilibrium. That's so it doesn't change composition when you ship it around to the world, which we'll get to the next. The details of this is within one of our MLMs here, 2574. Okay, so where did this occur? This is the gas mixing apparatus in the research building, which has non-radioactive things going on, and all the species here are non-radioactive. So somehow Ray got a Ruska DDR6000, and that was available to us, connected to this volume, which is water jacketed and has a water circulator here to define the temperature, stabilize it. And then there is the Toepler pump itself that adds each of these components to this volume. And then there's the controller. And the controller is here. And here's one of these start-stop boxes. When you press start to run it, stop to stop. So that's physically what it looks like. Now, there are lots of parts in here, some of which are never used. But it's just kind of a real estate problem of this is one of the areas that can be devoted to this thing, and it can do multiple functions. But you just keep all of the hardware together for each function. So it makes it look a bit cluttered, but Ray was flying it. So. Okay, so the products of this gas mixing system were 3 mixtures that were accurately prepared. These accurate mixtures were sent out to 7 different DOE sites that all had mass spectrometers that were supposed to be able to analyze mixtures like this. So the question is, how well can they analyze them? Because the accuracies of these mixes are like less than 1/4% uncertainty with them. They're that good. And so we were typically measuring with our own mass spectrometers somewhere between 1 and 2% of each individual component. Very useful, but not the degree that we wanted. And that is less than a 1% accuracy for any measurement that you do. This evaluation done by these mixtures at the 7 sites made a case for the fact that our mass specs were getting very old, and they were dated, and there are not anything modern. So the next thing we do is we get an agreement amongst all the participants on the spec for the mass spectrometer and go out on bid to all of the mass spectrometer builders in the world. The ones that bite are in England and in Germany. And so they started competing with each other, and they both wanted to be there. They both ended up selling instruments because they rose to the occasion and produced an instrument that actually met this 1% analysis requirement that we had put on it. And the measure that we had was to take these known mixtures and do acceptance tests on the new mass specs at the factory, so that if it didn't pass, you can fix it. And then before you ship it, it had to pass the analyses. There were 3 different mixtures that we would send. Okay. With all this automation of the gas handling systems and things like that, I think Ray had a little too much time on your hands. You were doing valves. No. Anyway, this is something that is work out of before. The idea of a a spherical valve tip, and a deformable seat on it. And the elements of this are, this is the plunger of the valve that gets injected. This is the seat that it seals against, and it's seated in here with O-ring seals on it. The whole thing can be assembled together to become a device that looks like that, or looks like this. Ray has one of these, and you can come take a look at it. And so that is a prototype that survived the decommissioning of Mound. Okay, so this is unique enough that in '84, or probably earlier than that, they filed for the patent on this, and it was granted. This is the patent number, and these are some of the seats that are considered as part of the claims in the patent. A few other observations that Ray has made in our discussions here, that how do you operate valves so that they don't leak and don't and last for a long time? These are examples of like a valve with a handle on it, and of course you close that, but Ray advocates for slow opening and slow closure of valves. And one way to do that is like fingertip tension, in which you grab the valve with your end fingertips, so you can't really put too much torque on it, and you just let it seat gently. This avoids over-tightening or the grinching factor. The other way, a preferred way, is to actually remove the handles and put on a hex head nut on it and a torque wrench. And that way, with the torque wrench set, you can close the valve with some torque. You can have some gorilla come and close it, and will produce the same torque. So it typically comes and starts slipping when you reach that torque point. So that's one way to extend the lifetime of valves. There are other bellows valves here that have air operators, some with large air operators and some with smaller ones, some with air to close and air to open. Most of them have a spring to close. So success in operating valves that have the spring closure on them is, first of all, gently open them by applying pressure, a gradient, and raise the pressure so it at some point opens. And then when you close, what you want to avoid is for the valve to go bang, close and deform the seat, make the system not seal well or get deformed. So the way you can do that is to throttle the gas that comes after you've opened it. You can control how the gas leaves the line that opened it, and it can cause soft seating of the valve on the way down. One way that earlier we saw the air lines that went to various valves in the systems are quite small. They're like 1/8 inch tubing, or maybe even smaller. And that's one way to throttle the pressure change and how fast the gas escapes, and keep it from banging. Some other thoughts about this is that the seat is typically softer than the stem tip. That's what's driven the source of our valves, which is Swagelok, to make stainless steel bodies and seat, and a stellite, which is a hardened stainless steel stem tip. Or you can use a polymer stem tip, either KELF, which does not tolerate tritium, but Vespel does, and either of them will make a seal. That's good. One other observation we've had is if the stem of the valve is not perfectly on the axis of the seat, you can end up with the valve, which is conical, making an ellipse on which one side you can generate leaks. So they're very, very small, but they can be there. Typically, they are sealed off at the factory. When we watched one of the valve inspectors, her last job was to take her finger and run it around the valve tip, presumably looking for rough spots, but also depositing body oils, which fills in the cracks, which makes them not leak. They pass tests, we get them, put them in tritium, and they start to leak. So those are things we have learned along the way. As the automatic Toepler pump was developed, there were other technologies that evolved here in the Dayton area. Daytronics Corporation down the road developed digital panel meters to read pressure transducers to 5 digits. And this was very valuable because the Ruska was actually had accuracies to 5 digits. There are also digital pressure and temperature gauges that became commercially available in the late 70s and early 80s. And the other thing that happened is 1975 to 1980, Motorola introduced its 6800 microprocessor system. And this was a computer that could be used for embedded control of instruments. So to that point, late in 1970s, Ray Baker and Richard Bauman began automation of the thermal decomposition system in SW219 that already existed, and they were going to connect the Motorola processor to this Al-Kaler actually wired it one weekend to the 6800, connecting valves and reading digital inputs and analog inputs. Ray programmed the logic and the sequencing of doing a decomposition run, and Richard Bauman used his experience addressing valves and helping with programming to make this operate as the first automated gas rock at Mound. During the 1980s, computers and process controllers improved, making the interfacing a whole lot easier, and full computer control of gas rack operations was there for the new dual gas rack that Ray and Richard worked on to develop. They chose an analog devices controller because it could be programmed in a higher level language called BASIC, and then the interfacing was easier to do without any wire wrapping or anything that can be part of the Motorola system. So this dual automated gas rack enabled 2 independent decomposition reactions to occur. So this allowed testing throughput to be basically doubled. This shows the physical layout of the 2 boxes. Since this was going to handle tritium within, the plumbing was first checked out with the hood fronts off, and you've seen pictures like this before where once you decide to put tritium in there, you put the hood fronts on with the glove ports and access to valves and things like that done through the glove ports. Just as a reference, there's 2 Toepler pumps here on this one side, and on the separate side there are 2 Toepler pumps here. So they're duplicate systems, and you can put the samples on and get it ready. Some of the support equipment for thermal decomposition, and that is over in this bay and that. And it's and a schematic of all of the glove or the interconnections of the valves and gas pads are shown here. The actual unit has a display of what the gas pattern is for interconnection, and there are little LED lights to tell if a valve is open or closed, either manually controlled, or you can follow what's happening with the computer control operation by looking at the pattern of valves that are open and those that are closed. And of course you need a pilot, and this is Ray Baker here working his machine on the initial checkout of it. So what happened? Because this was late 1989 when Ray was finishing this dual system. The fall of the Berlin Wall on the 9th of November in 1989 really had a major impact on Mound Laboratory. It changed the direction of its future. It signaled the end of the Cold War, and there was an expectation of a peace dividend which developed. So DOE in its response looked to various parts of the complex to see where can we close. And GEND and Mound were chosen as two sites that were relatively clean so that they are a good candidate for closure and decommissioning. So the Mound Lab closure was one of the sites chosen for downsizing. So in terms of this talk and this kind of thing, you've seen a lot of hardware that was developed and used, and in the glove boxes and that at work inside of the systems here. So what happened to the many Toepler pumps in use? Well, many were contaminated with tritium, and all of them had mercury in them. So together, a radioactive species and a hazardous chemical together defines a mixed waste. So during the decommissioning, all of the Toepler pumps were removed and were packaged and sent to Nevada RAD and mixed waste repositories. And so they are buried out there. No examples of unused parts still exist. We have an example of a valve, but we don't have an example of a Toepler pump. So if you know of where one might be staying, we would be very excited to see that and add it to our collection here at Cold War Discovery Center. So in summary, an all-metal Toepler pump was developed by Ray Baker with support from the skills and craftsmen, skilled labor and craftsmen at Mound. The Mound Toepler pump works very well, and it found many uses at Mound in different areas. The fact that it would operate automatically with an on-off switch made it valuable to many people. The pump and valve technology was unclassified, so publication was allowed. A publication in Review of Scientific Instrumentation contains an article that as to how the automated Toepler pump was put together, and for the all-metal version of it. The citation is there. There are other publications here at Mound that talk about the gaseous mixtures of hydrogen, deuterium, helium-3 produced by a partial pressure mixing system, and then the production of HD gas by the Toepler pump system. So all of those documents are here, and Ray's work on valve seats resulted in a patent granted by the, as a U.S. patent in 1984. And that you can look up like any patent using Ray's name and 1984. You'll find it in Google. Okay, before we end, I certainly want to thank Ray Baker for his creative ideas on how to automate a Toepler pump. First of all, make it all metal, and then automate it so that it will run and you just press an on and off button. That is what made it so useful and so widely used here at Mound. So we thank you, Ray, for all those creative ideas, and we thank you for your attention. So are there any questions? If you're seeing this on a video, you can email question to me if you have it at that address. Thank you.